Welcome to a new deep dive. Today we are not talking about slow code or finding bugs in JavaScript. We are tackling the theoretical ceiling of computation itself.
Yeah, the absolute fundamental mathematical limits of what a machine can ever automate.
This is really the bedrock of computer science, and it's where we gain the power to prove that some things are just impossible.
We are going right to the theoretical ceiling, yes, but we are also, equipping you with the ultimate intellectual tool for navigating it.
Hmm.
We've already met that monster before, that one uncomputable function that showed us computation has limits.
Right, but that first proof was, let's say, messy. It was all based on this complex self-referential paradox.
It was. And today we get a clean way to transmit that impossibility. We gain the ultimate weapon for proving unsolvability, reduction.
It's the tool that lets us take that one established impossibility, that foundational anchor, and use it to knock down dozens more complex problems. It's like dominoes.
It is exactly like dominoes. This method transforms a really hard theoretical proof into a clever logical translation problem.
Before we jump in, though, we have to simplify our targets.
We do. Our focus has to be on decision problems, basically simplifying any complex question into a fundamental yes or no answer. We just abstract away all the messy details and only ask, is this solvable?
I think the analogy helps a lot here. So instead of asking, calculate the exact landing trajectory for a Mars rover, you're just asking.
Will the rover land in the zone, yes or no?
Exactly.
It's a function that maps any input string, which represents a problem, into a simple binary output, 1 for yes, 0 for no.
And for a problem to be formally decidable, a couple of things need to be true.
Two things, absolutely. First, the algorithm has to halt. It has to stop in a finite amount of time for every possible input.
Every single one.
And second, it has to give the correct 1 or 0 answer. If the machine can't guarantee it will stop, or if it might get it wrong sometimes, then it fails. It's not decidable.
Right, I see. And this is linked to something called its characteristic function being computable?
Correct. If we can always calculate that function for sure, it's decidable. If there's even one input where the machine might just run forever, it's undecidable.
And the main technique we're going to master today is this reduction idea. We're going to internalize the logic of how you prove something is impossible.
The phrase that governs this entire deep dive, the one you should keep repeating in your head, is this. If I could solve B, I could solve A, but A is impossible, so B must be impossible too.
That's the mantra. We're going to apply that to everything from abstract logic to a surprisingly simple domino puzzle.
Exactly.
Okay, so before we venture into that terra incognita of the unsolvable, let's establish our baseline. What can be decided? We need a clear view of our safe harbor, the class we call REC.
REC for recursive or just decidable problems.
Yeah. So what's the first technical step?
The very first hurdle, and it's one that people often gloss over, is the coding constraint. Computers don't understand graphs or formulas. They understand strings of symbols.
Right.
So whatever we're analyzing, a graph, a number, a piece of code, it has to be translated or encoded into an input string for the machine first.
And we use those angle brackets for that, like GST, for a graph problem. That's literally the string of characters on the Turing machine's tape.
Exactly. And this brings up a really important question. Does it matter how we encode it? For instance, with a graph, you could just list all the edges as pairs.
Or you could use an adjacency matrix, which is just a long string of zeros and ones, and those two strings would look completely different.
They would look totally different, but for what we're doing today, for computability theory, they are equivalent.
Why is that?
Because the function that translates the edge list version into the matrix version is itself computable. You can write a simple program to do it, and it always halts. So since we can translate between them, the choice of coding is, well, it's irrelevant for whether the problem is solvable in principle.
Got it. We only really worry about how efficient the coding is when we get into complexity theory, which is a whole other can of worms.
A completely different deep dive. For now, we can just assume a standard encoding exists. But even then, any decision process has two steps.
Okay, what are they?
The syntax check and the content check. Step one is just asking, is this input string even a valid coding? Is it a properly formed graph, or is it just garbage?
If you feed it random characters, it should just say no and stop.
Right, and then step two is the real work. Does the content meet the criteria? Does the path actually exist in the graph?
And the good news is that for most of the problems we care about, the syntax check is kind of a solved problem.
It is. The set of valid codings for most things, like Python syntax or graph encoding, is what we call a context-free language. And we know those are efficiently decidable. We have parsers that can check the structure very quickly.
So we can basically ignore the syntax check and just assume the input is correct.
Exactly. We get to focus on the hard part, the mathematical core, the content check.
All right, let's ground ourselves with some concrete examples of decidable problems. What's a classic one?
The path problem. Super simple. Given a directed graph G, a start node S, and a target node T, is there a path from S to T?
That seems like something a computer should definitely be able to do, even for a huge graph.
And it can. The proof that it's decidable is straightforward. The graph is finite. You can't search forever.
You just use a standard algorithm like breadth-first search or something.
Yep, BFS or depth-first search. The algorithm just systematically marks every node it can reach from S. Eventually, it will have explored everything possible it has to terminate,
Right.
then it just checks. Was key marked? If yes, the answer is 1. If no, the answer is 0, 0. Always halts, always correct. Decidable.
Okay, that makes sense. What's another one? Maybe something a bit trickier.
How about the satisfiability problem, or SAT?
SAT. Given a logical formula, is there some assignment of true or false to its variables that makes the whole thing true?
Exactly. Now, SAT is famous for being incredibly hard to solve efficiently. It's NP complete, but
Yeah.
its decidability is absolute.
Why? Even if it might take, like, the lifetime of the universe to run?
That's the key. The proof hinges on finiteness. A formula only has a finite number of variables, let's say n. So there are only 2 to the n possible truth assignments.
And 2 to the 100 is an insane number, but it's not infinite.
It is not infinite, it's a finite number.
Yeah.
So, in principle, you can always write an algorithm that just builds the truth table and checks every single row one by one.
If it finds a row that works, it stops and says yes. If it goes through all of them and finds nothing, it stops and says no.
It always halts. Therefore, SAT is decidable. It lives squarely in our safe harbor, REC.
Which brings us to a really crucial property of REC, this lemma 1.26.
Yes, the property is this. A set M is decidable if and only if its complement, everything not in M, is also decidable.
So you get a 2-for-1 deal.
You do. If you have a guaranteed algorithm for a problem, you can get one for its opposite just by flipping the final yes and no answers.
So since SAT is decidable, its complement, UNSAT, the problem of checking if a formula is always false, that must also be decidable.
Correct. The moment we prove one is safe, we know its opposite is too. That's the comfort of REC. Now, let's leave these comfortable shores.
Okay, time to confront the monster. We're moving to the problem that forms the foundation for all of this. The halting problem. This is our unsolvable anchor.
This is the one we know for certain is unsolvable, and the one we will reduce everything else to.
It all started with a really specific kind of weird version, right? The special halting problem, or SHELT.
Yes, Schelt asks a very particular question. Given a program P, does that program terminate when you give it its own code as input?
The self-application scenario. It's like the computational version of the barber paradox. Who shaves the barber?
Exactly. And the big theorem here is Schelt is undecidable. And like all these proofs, we have to prove it by contradiction. We imagine a miracle machine exists that can solve it, and then show that this leads to total nonsense.
Okay, let's do it. Let's assume this miracle program, let's call it SHELT, actually exists. It takes the code of a program P, and it perfectly returns 1 if P halts on itself, and 0 if it doesn't.
So if we have this perfect Schelt program, this oracle, we can use it to build a new paradoxical machine. Let's call it SHELTNO.
And SHELTNO is built specifically to be a contrarian. It does the opposite of what the oracle predicts.
Precisely. Let's walk through what it does. SHELTNO takes some program P as input. First, it calls our miracle Schelt program on P.
Correct.
If Schelt says 1, meaning P will halt on itself, what does SHELTNO do? It does the opposite. It enters an infinite loop.
It deliberately refuses to halt. And if SHELT says 0 caught, meaning P will not halt.
SHELTNO does the opposite again. It immediately halts and returns 1.
Okay, I see the trap being set. The contradiction comes when we feed SHELTNO its own code, right? We ask, what does SHELTNO do when running on itself?
That's the moment the logic breaks. Let's trace it. Suppose SHELTNO halts when run on itself.
Well, by its own definition, for it to halt, the oracle SHELT must have predicted that it wouldn't halt. But that would have forced it into the infinite loop, so it can't halt. That's a contradiction.
Right. Now assume the opposite. Assume SHELTNO runs forever on its own code.
Then, again, by its own rules, for it to loop forever, the oracle SHELT must have predicted that it would halt. But that would have made it terminate. So it can't run forever either. Another contradiction.
It can't halt, and it can't not halt. The existence of Sheltno is a logical impossibility.
Which means our original assumption that the miracle Shelt program could exist in the first place must be false.
Exactly. That self-referential not proves it. Shelt is unresolvable. That function simply cannot be computed.
Okay, so that was the hard paradoxical proof. Now we get to use our new weapon, reduction, to go from that weird special case to the more general practical problem.
The general halting problem, HALT, which just asks, given any program P and any input N, does P halt on N?
This feels much more like a real-world question.
It is. And we don't need a new, complicated proof. We just prove HALT is undecidable by reducing the impossible problem we already have, Shelt, to it. We show that Shelt is, in a sense, easier than or equal to halt.
So Shelt is less than or equal to halt, is the notation.
Yep. And the reduction function, the translation, is almost trivially simple. It's beautiful. It takes the input for Shelt, which is just a program P.
And it transforms it into an input for halt. How?
It just creates the pair, the program P, and its own code P as the input. So the halting problem becomes, does program P halt on input P?
But that's just the definition of Shelt.
Exactly. The logic is perfectly preserved.
Yeah.
P halts on itself if and only if the pair PP halts. The reduction is completely computable.
And now we use the mantra.
Now we use the mantra.
If I could solve halt, I could solve Shelt. But I know Shelt is impossible. Therefore, halt must be impossible too.
And that's it. We've proven the general halting problem is undecidable.
So now that we have halt as our anchor, let's place it on the map of computability classes. We talked about REC, the safe harbor. Where does halt live?
Halt lives in the broader, more dangerous territory of A, which stands for recursively enumerable or semi-decidable.
Okay, what's the difference? REC is fully decidable. What does semi-decidable mean?
In R, if the answer to a question is yes, the machine is guaranteed to eventually halt and tell you yes. So for HALT, if a program does halt on an input, you can find that out by just running it. Eventually, it will stop.
But what if the answer is no?
That's the catch. If the answer is no, if the program runs forever, your simulation might also run forever. You never get a definitive no answer.
You're just stuck waiting. You could wait for 2 weeks and it's still running and you've learned nothing. It might stop in the next second or it might never stop.
That uncertainty is the defining feature of semi-decidability. A guaranteed yes, but no guaranteed no. Think of it like searching for a specific book in an infinitely large library. If you find it, you're done. If you don't find it after a million years, you don't know if it's not there or if it's just in the next aisle.
That makes sense. And REC is a subset of R where you get both, a guaranteed yes and a guaranteed no.
Exactly. And this also tells us something about the complement of arrow, which is the problem, does P not halt on N? We call it overline the HALT.
If article is an error, where is its complement?
Overline HALT is the classic example of a problem that's not even in RE. It's out in the true computational wilderness.
Why is that?
Because to prove that a program runs forever, you would need to simulate it for an infinite amount of time and then somehow stop and give an answer. It's logically impossible. You can't complete an infinite task in finite time.
I see. And because a problem and its complement both have to be in RE for the problem to be in REC, this confirms that HLA is strictly undecidable.
The boundary is mathematically rigid.
Okay, so we have our unsolvable anchor, HALT. Now we can really put the reductive mindset to work using it like a tool.
This is how we connect HALT to almost every other hard problem in computer science.
So let's unpack this. The idea is that we use a solver for some new problem, B, as a theoretical black box, right?
Exactly. You assume you have a magic machine that solves B. Then you show that you can use that machine to solve your known impossible problem, A.
Let's get formal for a second. When we say A is reducible to B, what are the exact rules?
Two things must hold. First, there has to be a function, let's call it f, that translates any input for problem A into an input for problem B.
And this translation function f has to be what?
It has to be total and computable. Total means it has to work for every single input. It can't just fail sometimes. And computable means an ordinary Turing machine has to be able to do it. The translation itself has to be an easy mechanical process.
You can't use a magical, uncomputable function to do your translation.
Right, that would be cheating. And most importantly, the translation has to preserve the answer. A, yes for A, must become a yes for B, and a no for A must become a no for B.
And if you have that, you get two huge implications.
Two massive ones. Case one is the positive use. If B is decidable, then A must also be decidable. You found a way to solve A by using the B solver.
Okay, that's useful. But the second case is our main weapon today.
Case 2, the contrapositive. If A is undecidable, then B must also be undecidable.
Because if B were decidable, then by case 1, A would have to be decidable too, but we already know A is impossible.
So B gets dragged down into impossibility with it. The logic is airtight.
Let's see it in action. Can we start with a positive example? Show how it's not always about doom and gloom.
Absolutely. Let's look at EMPT-NFA. The problem is, given a non-deterministic finite automaton, is the language it accepts empty? Does it accept no words at all?
An NFA accepts a word if there's at least one path from the start state to an end state. So the language is empty if there's no such path.
It sounds a lot like our path problem, doesn't it?
It really does.
So we'll reduce EMPT-NFA to the complement of path, which we already know is decidable. The reduction is simple. You just convert the NFA into a graph, the states become nodes, the transitions become edges.
And the question, is the language empty, becomes, is there no path from the start node to any end node?
Exactly. Since we know no path is decidable and the translation is clearly computable, then EMPT-NFA must be decidable too. We used reduction to find a solution.
Okay, that's a nice positive one. How about a quick detour into complexity? I know you mentioned indiset and set.
Right, indiset is given a graph G and a number K. Is there a set of K nodes where no two are connected by an edge? We can reduce this to SAT to prove it's decidable.
How does that translation work? You're turning a graph problem into a logic problem.
You build a massive logical formula. You create a variable for every node in the graph. The formula has to enforce two things. One, that exactly K variables are true.
Meaning exactly K nodes are in the set.
And two, for every single edge in the graph between two nodes, say I and J, you add a clause to the formula that says, not node I is true and node J is true.
You can't have both nodes in the set if they're connected. That perfectly captures the rule of an independent set.
It does. And since we can algorithmically build that formula and we know SAT is decidable, it proves indiset is decidable too.
Okay, now back to the main event. Using reduction to prove impossibility. Let's knock down a new problem.
Let's take down the inclusion problem, or INCL.
What's the question for INCL?
Given two programs, P1 and P2, is the domain of P1 a subset of the domain of P2? In plain English, does P2 halt on every input that P1 halts on?
This sounds tricky. So we want to show that HALT can be reduced to INCL.
That's the goal. We take an arbitrary instance of HLT, a program P, and an input N, and we need to transform it into an instance of INCL, which is two programs, P1 and P2.
How do we construct P1 and P2?
P2 is easy. We just set P2 to be our program P from the HALT problem. Now, P1 is where the clever trick comes in.
Yeah.
You got to construct P1 to isolate just the single input we care about, N.
So you create a special program.
We create a program called, say, Ponleon. This program does one thing. If its input is N, it halts immediately. For any other input, it goes into an infinite loop.
And that's a simple program to write?
Trivial. So the domain of Ponleon, the set of inputs it halts on, is just a single value, N.
Okay, so P1 is Ponleon and P2 is P. Now we ask the INCL question. Is the domain of P1 a subset of the domain of P2?
Which is the same as asking, does P2 halt on the input N?
Which is the same as asking, does P halt on N? That's the original HALT problem.
We did it. We reduced HL to INCL. The conclusion is inescapable. Since HL is undecidable, INCL must be undecidable too. And that little trick of creating a program with a tiny domain is one of the most common tools in these proofs.
Okay, wow. Here's where it gets, I think, really interesting. We're going to apply this whole mindset to a completely different area. We're leaving programs and logic behind.
We are. We're turning to a seemingly harmless puzzle called the post-correspondence problem, or PCP.
This feels like a critical moment. If we're going to show that this impossibility thing is contagious, it needs to be able to jump from abstract machines to something tangible.
And PCP is perfect for that. It was proposed by Emil Post back in 1946, and it's basically a domino puzzle.
So what's the setup?
You're given a set of dominoes, but instead of dots, they have words on them. Each domino has a top word and a bottom word.
And the goal is to line them up. How?
You have to pick a sequence of these dominoes. You can reuse them as many times as you want, so that when you concatenate all the top words together, you get the exact same string as when you concatenate all the bottom words.
You have to make the top string and the bottom string match perfectly.
Let's use our example. Stone 1 has 1 on top and 111 on the bottom. Stone 2 has 111 on top and 10 on the bottom. Stone 3 has 10 on top and 0 on the bottom.
So as soon as you pick 1, you create a mismatch. If you pick stone 1, the top is 1 and the bottom is 111. The bottom is already ahead.
Exactly. So your next choice has to be strategic. You need to pick a domino that helps the top string catch up.
And in this case, we know the sequence 2, 1, 1, 3 works. It creates the matching string 101, 1, 11, 1, 10.
It does. So this particular puzzle has a solution. But the crazy thing is, the general problem of PCP is undecidable. You cannot write a program that takes any set of dominoes and tells you for sure if a solution exists.
But why? It seems like you could just try combinations.
Because the length of a potential solution is unbounded. The shortest solution might be a sequence of 10 million dominoes. How long do you search before you give up? After trying for a year, you don't know if you're close to a solution or if one simply doesn't exist.
You can't guarantee that the no answer will ever terminate.
That's the heart of it.
Okay, so this is the master reduction. We have to show how this simple domino puzzle can perfectly encode the entire computation of a Turing machine.
We take an arbitrary HALT instance, a machine M, and an input word W, and we algorithmically generate a specific set of dominoes. And the construction has to be so precise that a solution to the domino puzzle exists if and only if the machine M halts on W.
How on earth do you do that? How do you force a sequence of dominoes to tell a story of a computation?
The core idea is ingenious. We force the bottom string on the dominoes to always lag one computational step behind the top string. The top string represents the current state of the machine, and the bottom string represents the next state.
Okay, so a configuration of a Turing machine is the tape, the head position, and the current state. You encode all of that as one long string.
Exactly. And we need to build the specific dominoes that will simulate the machine steps. Let's start with the first one.
The start stone.
The start stone. This one has to set up the initial state and create that crucial one-step lag. We use a special separator symbol, hashtag. The top of the stone is just hashtag.
And the bottom?
The bottom is hashtag, then the starting state Q0, then the input word W. So right from the start, the bottom string has a huge head start. The entire puzzle is now about finding a way for the top string to catch up.
And it can only catch up if the computation halts. I'm starting to see it.
Now for the main work, the stones that simulate the machine's moves. Let's say the machine has a rule. If you're in state P reading symbol A, you should write symbol B, move the head right, and go to state Q.
A standard right move transition?
For that rule, we create a domino. The top is PA, the bottom is BQ.
So the top consumes the old state and symbol, and the bottom spits out the new configuration.
And it perfectly simulates the head moving right. What about a left move? That's a bit trickier. Because if you move left, the new state symbol has to appear to the left of where the head was. So the domino needs to look at the symbol to the left as well. If the symbol to the left is C, the domino would be top CPA, bottom QCB.
Wow, so you need a different domino for every possible symbol that could be to the left.
You do. It generates a lot of dominoes, but it's a completely mechanical process. And this forces the sequence of choices to perfectly mirror the deterministic steps of the machine.
But what about the rest of the tape? The parts the head isn't touching.
That's where the copy stones come in. They are crucial. For every single symbol A in the tape alphabet, you create a domino that is just on top and on the bottom.
The identity domino.
Right, and these just copy the unchanged parts of the tape from the current configuration, top string, to the next one, the bottom string.
So as long as the machine is running, the top and bottom strings grow, but the bottom is always one full configuration ahead, separated by that hashtag. If the machine never halts, they just grow forever.
And the top can never catch up. This brings us to the end game. The termination stones.
This is how the gap gets closed.
The only way the puzzle can be solved is if the machine enters a final halting state, let's call it Q. Once that state Q appears in the string, a new set of dominoes becomes usable. The cleanup stones.
What do they do?
They do the opposite of all the other stones. They make the bottom string shorter than the top string. For example, a cleanup stone might have ACH on top, but just Q on the bottom.
It eats the symbol next to the halt state.
Exactly. You use these repeatedly to chew up all the leftover symbols on the tape until only the state itself remains.
And the genius here is that these cleanup stones are only usable if the machine actually reaches the halting state Q. If it loops forever, you can never use them, and you can never close the gap.
That's the whole proof. Once the tape is clean, you use a final stone to match the remaining hashtags, and the top and bottom strings become identical.
So if the machine halts, you have a finite computation history, which gives you the sequence of dominoes to solve the puzzle. If it doesn't halt, no such sequence exists.
And there it is. H-alt reduces to PCP. Since H-alt is undecidable, PCP must also be undecidable. This simple domino game is just as hard as the halting problem.
That is incredible. The fact that you can hide that kind of infinite complexity inside a simple string matching game is just mind-blowing.
And now we can see the practical consequences. This isn't just a theoretical game. This impossibility is contagious, and it infects almost everything we try to do in software engineering.
Right. Because if we could solve the domino puzzle, we could solve H-alt. And since we can't, it means a lot of the tools we wish we had are mathematically impossible to build.
Let's list a few. The equivalence problem. Given two programs, do they compute the exact same function?
That seems like something you'd want to know. Is this new optimized code really the same as the old one?
You'd love to know that.
Yeah.
But it's undecidable. You could reduce HL to it. If you could solve equivalence, you could check if an arbitrary program is equivalent to a program that just loops forever.
And that would tell you if it halts or not. Okay, what else?
The correctness problem. Does my code do what the specification says it should do? This is basically the same as the equivalence problem or the ion seal problem we saw earlier. Impossible in the general case.
And what about the dead code problem? Will this specific line of code ever get executed?
Also undecidable. We can use that same isolation trick. You take a program P and input N, and you build a new program P prime that first simulates P on N. If that simulation halts, then it executes the line of code you're interested in.
So the line is executed if and only if P halts on. If you had a dead code checker, you'd have a HALT solver.
Which you can't have. So even something that feels like a simple structural analysis of code is actually tied to its deep semantic behavior.
This all leads to the big one, the practical one everyone has on their computer.
Yes.
The antivirus conundrum.
Yes. The impossibility of a perfect antivirus.
You'd want a program that could take any file and tell you for sure, is this malicious? Does it do something bad, like delete your files?
But deleting files is a semantic property. It's about the program's behavior. And we could use the exact same reduction. We construct a program that first simulates P on N, and if it halts, then it does the malicious thing.
So asking the antivirus, is this program malicious, is the same as asking, does P halt on N?
And since we know the answer to that, we know a perfect antivirus that can analyze the behavior of any arbitrary new program cannot exist.
So what do current antiviruses do?
They cheat. They look for known patterns or signatures. That's a syntactic check. Or they run the code in a safe sandbox and watch what it tries to do. But they can never give you a 100% guarantee about the semantic intent of arbitrary, unseen code.
This all seems to be building up to one big, devastating general rule.
It is. It's called Rice's theorem, and it's the theoretical sledgehammer that covers all of this.
Okay, what does it say?
Rice's theorem states that any non-trivial semantic property of a program is undecidable.
Let's break that down. Semantic means it's about the program's behavior, what it does, not what it looks like.
Right. Does it output a prime number? Does it access the network? Those are semantic. Does it have more than 10 lines of code? Is syntactic. And that's easy to check.
And what does non-trivial mean?
It just means the property isn't true for all programs, or false for all programs. There has to be at least one program that has the property and one that doesn't.
So basically, everything we actually care about in software correctness, security, termination, is a non-trivial semantic property.
Exactly. And Rice's theorem says that any tool that claims to automatically and perfectly check for any of those properties for all possible programs is a pipe dream. It cannot be built.
So what do we do? For really critical systems, like in an airplane or a medical device, you can't just guess.
You can't. The engineering response is to restrict the universe. You don't try to solve the problem for all programs. You prove correctness by hand using formal methods, which is incredibly difficult and expensive.
Or you use a less powerful programming language on purpose.
Precisely. You use languages that don't have features, like general recursion, things that could lead to infinite loops. You sacrifice expressive power in exchange for certainty. You pull the problem back into the safe harbor of REC.
This all comes back to that distinction between REC and RE.
It does. In the real world, we often have to settle for semi-decidability. When we're testing software, if there's a bug, we might eventually find it. That's the yes answer.
But if we run tests for 10 years and find nothing,
We've learned very little. We can never be certain that the software is perfect. The absence of evidence isn't evidence of absence. This leads to the hard lesson of theoretical computer science.
that testing can prove the presence of errors, but never their absence.
Right. So we established that logical rule. If I could solve B, I could solve A, but A is impossible, so B must be impossible too. That's the engine that drives all of this.
We took that initial weird self-referential paradox of the halting problem and showed that its impossibility is contagious. We watched it jump to a seemingly simple domino game, the post-correspondence problem.
And that master reduction, forcing those little string puzzles to perfectly mimic the history of a Turing machine is just, it's a breathtaking piece of theory.
And from there, the impossibility infects everything we do in programming. Writing a perfect bug checker, guaranteeing security, making an antivirus. We haven't proven that computing is pointless, but we have drawn a very clear line in the sand.
We've defined the mathematical ceiling of what automation can ever hope to achieve.
And knowing where that boundary is forces us to be smarter engineers. It tells us not to waste our time chasing magical tools that can't exist.
The insight is in accepting the limits and designing our systems to work within them.
Now, for a final provocative thought for you to chew on, it turns out that you can keep producing. The undecidability of PCP can be reduced to the undecidability of formal logical truth. Specifically, the problem of deciding if statements in first-order logic are universally valid. So if the problem of deciding what is logically always true is fundamentally unsolvable by any algorithm, does this imply that absolute certainty itself, even in the pure world of math and logic, might require something non-mechanical, something beyond mere computation, something to think about until the next deep dive?